Hi, good morning, everybody. Before I begin, I'd like to thank the organizers of MuniHac for giving me an opportunity to speak here. I love coming to Munich. Every time I come here, it's a wonderful city, and I really enjoy being here with everybody. And today, I'll be giving a talk on beautiful folds. And so, if you've never heard of beautiful folds before, I'll motivate them by saying that they're something that commonly arises when we do parallel or distributed computation, especially in big data. In fact, a lot of what I'm going to be talking about from here, I've basically stolen from my experience doing big data at Twitter. And this talk will explain the basic underlying abstraction that we'll use to translate this to Haskell, and also explain really cool tips and tricks for how to use this abstraction even when you're not doing big data or parallel processing. So I don't expect you to understand all these lines of code immediately up front. I'm going to introduce them slowly as the talk goes on. The point of the slide is basically to illustrate that everything in this talk can be condensed to just 14 lines of Haskell code. So this is so short that you could literally just paste it into your project and use what I'm talking about without even a library. Most of this talk is just going to be explaining what these 14 lines of code mean and what are the implications of what you can do with this code. Before I begin, so the outline of this talk is I'm going to begin by talking about basics of how this fold abstraction and type works. And then I'm going to move on to non-trivial folds that you can rise to power very interesting analytics over data. And then I'll talk about how folds can be composable. So you can take smaller, focused folds that do one thing and do it well, and you can combine them into larger and more complex folds. And then I'm going to show how you can actually use these folds in multiple ways, and lots of really clever and interesting ways as well. And then the last part of the talk, I'll show how you can have folds focus in on subsets of the data and give some practical examples of that. So the trick I'm describing is not something I came up with. It's not novel. In fact, the actual term for this talk is something that somebody else coined, Max Rabkin, back in 2008, although I'm pretty sure this abstraction precedes even that. I didn't do any archaeology further back than that. So in industry, probably the most widespread use of this abstraction is in Scala's algebra library, which is what Twitter uses for big data processing. And it's kind of similar in principle to MapReduce programming if you squint a little bit. The analogy is not exact, but it's close. But the key thing I want to drive home in this talk is that this is a useful abstraction even if you don't do parallel or big data processing. So here's the simplest bit of code that actually does something contrived. So I'm going to define a data type called fold, which has two type parameters named I and O. I is short for input, O is short for output. And then there's a third type parameter which is hidden from the user. They don't actually see it when they use the fold type. And I'm going to call this type M, which is short for monoid. And the reason why is that there's no restriction on what this type can be other than it must implement the monoid type class. And this fold type is actually very simple. It has only two fields, both of which are functions. The first function just transforms an input of type I to an intermediate monoid of type M. And the second function transforms the intermediate monoid of type M to an output of type O. And that's it. That's the entire fold type. And it turns out we can do a lot of clever things with just a record of two functions. One of those things we can do is we can use it to fold a list. So for example, if I have a fold from i's to an O, then I can take a list of i's and I can fold it down into a single O. And the way this works is that we're going to take each I, we're going to transform it to a value of type M, and we're going to have a list of m's, all of which are monoids. And if you're familiar with Haskell's prelude, it provides an mconcat function, which you can use to collapse a list of monoids into a single monoid of type M. And then we can just use our second function to transform that M into our final output of type O. And that's what this function is doing. So I like to call these two functions tally, the one from I to M, and summarize, the one from M to O. So we map our tally function over the list of i's. And this reduces basically the same as mconcat from the prelude. It's just a strict version. In this case, it's because I don't want any space leaks. And then after I reduce the list, I just summarize the final result. And as a very simple example of how we use this fold function, we need to actually provide a real fold. And so I'm going to provide a fold called sum. And I'm going to hide the sum from the prelude. So anytime in these slides you see sum, assume it's the fold and not the function on list from the prelude. So this sum fold has a very simple tally function. It just wraps each input element in the sum monoid, so that when we combine elements, we add them. And then the summarize function just unwraps the sum new type to get us the final result. So for example, if I pass this sum fold to the fold function and I sum all numbers from 1 to 10, it'll give me back 55, which is the correct answer. And if I sum a billion numbers, it can go through the list at a rate of about 0.3 nanoseconds per element, which is pretty efficient. And to give you an intuition how to work, we'll do a quick equational reasoning exercise just to work through what's happening under the hood. So we start with fold, sum, and a list of 1, 2, 3, 4. And then the second step just replaces the sum fold with its definition. It's a fold whose tally function is the capital S sum, and whose summarize function is get sum. And then we basically apply the definition of fold, which says that we summarize, we reduce, we map tally, and then we reduce, and then we summarize, where tally is the sum function, and summarize is the get sum function. And then reduce is just a strict mconcat. And then we just map the sum function over the list. So now we replace 1, 2, 3, 4 with sum 1, sum 2, sum 3, and sum 4. And then finally, we mconcat the list, essentially. So now we just map-end all these sums together. Mempty is just sum 0. And then if we add 0 plus 1 plus 2 plus 3 plus 4, using the monoid instance for sum, we get sum 10. And then get sum just unwraps the result, giving us print 10. So that's what happens when Haskell evaluates an example sum. Any questions before I move on to more complex examples of folds? Yes?
Do you use this form of equational reasoning when you write code?
So the question.
Just now when you're explaining it?
The question was, do I use this form of equational reasoning when I write code, or just when explaining it? I actually do use this when writing code all the time. And the reason why is because I like to prove things about my code, like high-level laws. And the way I do so is by equational reasoning of this sort. I don't think I did that particular equational reasoning like in practice, but there are other examples where I have. And I can actually call those out later on the slides as I go on. Any other questions? So here's a more interesting example. Let's say I want to compute the average of all numbers in the list. So the way I can do that is I can just keep track of a numerator and a denominator as I'm reducing results. I'm going to define an average type, which just has a field for a numerator and a field for a denominator. And I'm going to give it a monoid instance, where when we combine two average functions, we just add their numerators, and then, two average data types, we combine their numerators, and then we combine their denominators. And then at the end, when we're done adding up these average data types, we just divide the numerator by the denominator to get the final result. So our tally function will take each input value, named x in this case, and we'll just wrap it in an average data type where x is the numerator and 1 is the denominator. And then we'll add up all the averages, and then at the end we unpack our average and just say it's the numerator divided by denominator, using from integral because the denominator is an integer. So for example, if I average all numbers from 1 to 10, I get 5.5. And if I average all numbers from 1 to a billion, then I get, I don't know, 5 billion and something. And probably a bunch of rounding errors in there due to floating point arithmetic. And it goes through the list at 1.3 nanoseconds per element too. And not only does it go through the list pretty efficiently, but it also does so without any space leaks whatsoever. So here is actually a heap profile of our example average fold. And the maximum redundancy is, I think, 35 kilobytes of memory, which is pretty good. In fact, this is basically the lowest maximum redundancy you can get for a GHC program. It's basically using nothing at all. This is all the GHC runtime, essentially. And we can perform the same equational reasoning exercise. I'll skip the first few steps, which are basically the same as the original example. The only difference is now our tally function will take 1, 2, and 3 in this case and replace them with average 1, 1, average 2, 1, average 3, 1. And then we just have to add all these averages together using their monoid instance. So we just end up summing all the numerators, which are 0, 1, 2, and 3. So we get 6 for the new numerator. And then we sum all the denominators. So 0, 1, 1, 1, which is 3. So our final average at the end is average 6, 3. And then we just divide 6 by 3 to get the actual average, which is 2. In fact, you can actually take everything in the data.monoid module and you can turn it into an equivalent fold. For example, if you're familiar with the first monoid, you can use that to write a fold named head, which is a safer version of Prelude's head. And so this will give you the first element in whatever your input list that you're folding. Then the last monoid becomes the last fold. And then the all monoid can be used to define an all fold, which tells you if all elements satisfy some predicate. The any monoid can be turned into the any fold, which tells you if any elements satisfy a given predicate. Then you have a sum fold and a product fold. And the length fold, what we just do is we transform each input element to some 1. And so then we just add up all these 1s to get the length of the list. And this just shows that they work. So the head of 1 to 10 is 1. The last of 1 to 10 is 10. Not all numbers are even, but there are some numbers that are even. And then you can sum them, you can multiply them, and you can compute the length of the list as well. Here's a more interesting fold. So let's say I want to compute an exponential moving average of a collection. So this is like an ordinary average, except it's biased towards more recent element. And you can tune how biased it is with a constant factor called alpha. This particular one is hard-coded to a specific alpha constant, which is 0.3. And the 0.7 is 1 minus alpha in the equation. And so the way it works is you have a data type which keeps track of 2 fields. The first field is the number of samples you've seen so far. The second field is the current estimate of the exponential moving average for all the values that you've reduced. And then we have a way of combining them. So ignore this top part. This is purely here as an optimization for efficiency, and just focus in on this bottom part. So if we add together 2 exponential moving average data types, we just add up the number of samples. And then we combine their averages, but weighting towards the newer one. So we actually weight against the older samples, and then just taking account how many of the newer ones there were to calculate how much we should weight against the older ones. And you can actually go through the exercise and show that this implementation satisfies the monoid law. So this mappend is associative, and this mempty is its identity. And then if we want to fold the list, we just take each input element, and we transform it into an exponential moving average data type with 1 sample, and where that element is the current estimate of its average. And then after we're done reducing the list using the mono instance, we then just unpack the data type, we throw away the number of samples, and we use the value as the current average. Multiplied by 0.3 because you need that to get the correct formula. So for example, in this case, I use an alpha constant of 0.3. So on average, it means we'll be biased towards the most recent 3 elements that we've seen. So if I fold all numbers from 1 to 10, I get something that's approximately 8. If I fold all numbers from 1 to a billion, I get something that's approximately a billion minus 2. And it goes through the list at 2.6 nanoseconds per element. Here's another interesting one. So if you ever work in a big company like Google or Facebook or Twitter, you're going to get a very common request, which is count the number of unique visitors, because they obsess over the number of unique visitors that they get, because that's how they live and die and sell themselves to investors. So if you try to answer a question like number of unique of anything, the way you might commonly answer it is in terms of a set, right? So this is a very dumb way of doing it. So we say we take each input element, we wrap it in a one element set, a singleton set. And then we mappend all those singleton sets together to get the combined set. And then at the end, we just ask how big that set was using its size function. And that's how many unique elements that we had for our input. And the problem with this is, though, is that it requires a potentially unbounded amount of memory. So if you have like 1 billion users to your site, then you're going to have a set with 1 billion elements in it, which is not good for performance and not good for space usage. But there's a more robust algorithm you can use that gives an approximate estimate of the number of unique elements in a set. And this is called the Hyperloglog algorithm. This code right here is not the real Hyperlog algorithm. It's a very simplistic version that is just for teaching purposes and fits on a single slide. This will just give you the basic idea underlying how the simple version works. And there's a real Haskell package that provides the fancier, more statistically robust version. And that's Edward Komet's Hyperloglog package. I'm going to teach the really simple version. So the way the simple version works is that we hash every element to a sequence of bits. In this case, I'm going to hash them to 64 bits, just for simplicity. And then what we do is we see what's the longest consecutive prefix of zeros in all those elements. And the reason we care about that is that longer prefixes are going to be increasingly rare. For example, on average, if all your 64 bits are completely random, then you'd expect that half the time you have no zeros in your longest consecutive prefix. And then 1/4 of the time you'll have 1. And then 1/8 of the time you'll have 2. And then 1/16 of the time you'll have 3, and so on. So the longer a prefix that you see in your set, the rarer it must be, and the more unique elements you must have had. In fact, you can basically, every additional 0 roughly doubles your estimate of the size of your set. And that's what this algorithm is implementing. So under the hood, we're going to use a max monoid, where whenever we map-pen to elements, we just take their maximum. And then the way that we will compute the number of uniques is first we have to provide a hash function, which transforms each input to a 64-bit word. And then, reading from right to left, so we hash x to give our word 64. And then the GHC provides a primitive operation for counting the number of leading zeros from word 64, so that's efficient. And then we just wrap it in this max function. So this is how many leading zeros we had for each individual x. And then when we map-pend all of them, we get the longest leading prefix of zeros in our input set. And then we just raise 2 to that prefix to get the estimate of the set size. So for example, here, I have an example program where I just generated 10 random integers. They go off the end of the slide. And then I create so I cycle that list of 10 integers to create a list of 1 billion integers, and then ask this fold to compute how many unique integers are there in that list of 1 billion. And the reason I just did 10 is because, surprisingly, if you go up to about 20 word 64s, then GHC actually panics in its simplifier phase. And I'm going to open up a bug report for that. I have a very small reproducing test case for that now. But anyway, so if you ask this fold, how many unique elements are there in this set of 1 billion, which are really just the same 10 repeated over and over, it'll estimate there are approximately 16 of them. And it does so at a rate of about 5.5 nanoseconds per element. Yes?
If it says 16, wouldn't it also say, like, with a certain probability it's actually 32 or 8?
So this doesn't do that, but Edward Komet's Hyperloglog package does. So the question, sorry, to repeat the question was, instead of 16, shouldn't it say something like x16 with this probability or with this confidence interval, like spanning from over some range? So the simple version I implemented doesn't do that. But Edward Komet's Hyperloglog package does do exactly what you asked for. So it returns not just a single value as its result, but an approximate value, which is basically a range with a confidence interval. That's why I say that his version is the fancier and more statistically robust version. So I would like to present more examples of more complex folds, but Haskell doesn't have them. But in Scala's algebra library does. And so if somebody's looking for a really high-value Haskell project for analytics or big data, it would be just to port all of these folds that I'm about to describe from the Scala ecosystem to the Haskell ecosystem. So for example, in the algebra library, there's a quantile digest monoid, which you can use to implement approximate medians, percentiles, and histograms. There's a countmin sketch monoid, which gives you approximate estimates of like the top n most frequently occurring elements. There's a stochastic gradient descent monoid for computing distributed linear regressions, which is actually pretty cool. There's a monoid for Bloom filters, which are commonly used for approximate membership testing. And algebra even provides a type which is analogous to the fold type that I'm describing, but in algebra it's called an aggregator type. And it actually has an applicative instance exactly equivalent to the one I'm about to show later on. And as far as I know, these have not been ported to Haskell, and I would really love somebody if they were to port them. I would thank you. I would be very grateful. So are there any questions before I go on to the next segment of the talk, which is how to compose multiple folds into a single fold? No? OK, good. So very often when we analyze a data set, we don't want to analyze just one thing. We usually want to analyze several things at a time. So we might want to provide a function like combine, which given two folds, so a fold from I to A and a fold from I to B, combines them into a single fold from I to A and B. So in other words, we want to compute these two folds in one pass over the data set simultaneously. And this is actually a very simple function to write. So our two input folds each have their own tally and summarize function. I use L for the left folds tally and summarize function, and R for the right folds tally and summarize function. And so the combined folds tally function just delegates to the tally functions of the left and right fold and just stores the result in a tuple. And this works because we know that this tally function returns some monoid. We don't know which one, but it returns something that's a monoid. Similarly, this tally right function returns some monoid. We don't know which one, but we know it's a monoid. And therefore, this is a tuple of two monoids. And the Haskell prelude provides an instance that says that if the two fields of a tuple are a monoid, then the tuple itself is a monoid, and it does the right thing. And so after we reduce all these tuples of two elements in our list, then we're ready to summarize them at the end. So we just deconstruct the tuple, and then we just summarize the left and the right element, delegating to the summarize function for each individual fold that went in. So for example, let's say I want to compute the sum and the product of all numbers from 1 to 10. Then that gives me the result 55 for the sum and a large number for the product. And we can actually generalize this combined function by making the full type implement the applicative type class. So I'm going to skip over the functor instance and just focus on the applicative instance. This applicative instance is almost identical to the combined functions. Like the tally part is actually identical. And the summarize function is the part where it slightly differs. So instead of returning a tuple of our two summarized results, we actually apply the first one to the result of the second summarize function, because that's how the app function works. It's the only thing that type checks, so you couldn't get it wrong. And the pure function is just a fold that ignores its element, all its input elements, and it uses the mono instance for unit to do absolutely nothing. And then it always returns O every time. And we're actually going to make one slight tweak, which is that in order to avoid space leaks, our internal tuple, two tuples is actually going to be, we're going to replace it with a strict pair. That's the only change I'm going to make. And this is just so that we can very efficiently not leak space. And so armed with that new applicative instance, we can then implement combine in terms, it's just lift A2 and then the two tuple constructor. And in fact, this definition is so general that we can just use the type that's inferred by the compiler, which now works for any applicative as opposed to just full. So this combine function just became much more useful by formulating in terms of applicatives. And we don't even have to even use this combine function, right? We could just inline the fold that we want using the applicative operator. So we can say fold both the sum and the product, and then that gets us our result at the end. So this is a very nice way of combining folds together. So now I have a question for you all, which is that there's an anti-pattern that I see very often in the Haskell ecosystem, which I'm going to sort of sum up with this bad function at the top. So this bad function takes an input list of doubles, and then it returns the sum of all the doubles and the product of all the doubles. And then this good function is the equivalent version using the fold functions that I've just presented. So my question for the audience is, what is wrong with the bad function at the top, and why is the good function better? Yes?
Well, it builds up all elements, and then it combines them.
Yes.
While the other one does it linearly.
Yes. So the correct answer was that the bad function will materialize all the list elements into memory, whereas the good version will only process one element at a time. It'll never materialize more than a single list element in memory because it processes all the elements in lockstep. If you're new to Haskell semantics, the reason why the first one materializes the whole list is because normally, if you were to just sum a list and you didn't care about the product, what would happen is every time the sum is processing a new element of the list, after it's done with that element will be garbage collected because the Haskell runtime will detect, oh, hey, there are no more references to this element, so I can just get rid of it. But when we throw in this product keeps holding on a reference to these x's, so the Haskell runtime cannot garbage collect them. And so if you evaluate either the sum first or the product first, either way, you're going to end up materializing the entire list. This version doesn't leak because it processes both folds in lockstep for each element. So you can always garbage collect each element after it's done, no matter how many folds you're computing. This is one of the reasons why I say that the fold type is useful even if you're not doing parallel or distributed programming, because it lets you compute multiple folds in one pass without ever materializing the whole list, which again also improves the efficiency of doing multiple folds. And we can use this applicative instance to do more than just comparing up fold results. We can use it to define more complex folds from simpler folds. For example, I can now define the average fold in terms of the sum fold and the length fold. I just say divide the sum by the length, and that's your average. And the code it generates is absolutely identical to the handwritten version that I presented on an earlier slide. So if you fold all numbers from 1 to a billion, it takes the exact same amount of time and computes the exact same result. And because everybody asks me this when I present about averages, there is, in fact, a numerically stable average that also has a monoid instance. I'm not going to go over this other than to point out like it does exist. And I will host these slides later in case you want to refer to this and see how to implement it. But there's a numerically stable way of implementing averages using monoids. Another cool thing about folds is that, in fact, this is true for any data type that implements an applicative instance, is that you can also go ahead and implement an instance for Haskell's numeric type classes, specifically num, fractional, and floating. And the way we do this is we just use the applicative operations to lift every operation. So every unary operation, like negate or abs or signum, we just lift them using fmap. And for every binary operation, like plus, times, or minus, we just lift them using lift A2. And then we just repeat that for every single operation in these 3 type classes. That's all you have to do. And once we have these numeric operations and folds, we can actually do very cool things with them. For example, I can fold the length minus 1. So that 1 there is not an integer, it's a fold. So I'm subtracting 1 fold from another fold. So if I apply that fold to a list, it will obviously get me the length minus 1, which in this case is 9. I can also define average more succinctly. So I can say now that the average is just the sum divided by the length. I don't need applicative operations anymore. So that's a very high level way of specifying the average. So if I fold the average over a list, I get 5.5 still. And again, this is exactly the same code as before, exactly as efficient. I can even take the sign of a fold. I can exponentiate a fold, and I can add them. So like this uses the well-known trigonometric law that sine squared plus cosine squared of anything is going to be 1. So I just pass an average just for fun. And of course, it returns 1. It doesn't really use the average. Oh, yes?
That num instance.
Yeah.
Assuming no undecidable instances problem or whatever.
Yeah.
Can you define it for any applicative?
So the num instance, so the question was, can you define that num instance for any applicative? The answer is yes, although for some applicatives, it may give unexpected results for subtraction. An example would be the list applicative, right? You'd expect that x minus x equals 0, but for lists, that doesn't exactly give the right behavior you would expect. For folds, it does. So this is one case where it is well behaved with respect to the num laws. But in practice, that applicative instance, which I introduced, will type check for any type that implements applicative, and it will work.
It will not respect the...
Yeah, it will not necessarily respect the group laws for subtraction or negation. If you were to get rid of all subtraction or negation results from the num type class, then I believe then they would all be well behaved. I think. Don't quote me on that or be totally pedantic about it. But so you can also pass a numeric literal any word that expects a fold. So if I just fold 99, it's just going to ignore the input and always return 99, which is what happens here. Here's a more interesting example. So Wikipedia has this formula for how to compute the standard deviation of an input set. I'm going to use the rightmost equation from this diagram that I stole from Wikipedia. So it says a standard deviation, you begin by computing the sum of the squares, then you divide by the length, and you subtract from that the sum divided by the length squared, and then you square root the result. And then the translation in terms of folds is going to read almost exactly like the original mathematical equation. You just have to define an intermediate helper function to compute a helper fold to compute the sum of squares. And so we just say the sum of squares divided by the length minus the sum divided by the length squared. And then you just take the square root of that. And so I'm dividing folds, I'm subtracting folds, I'm exponentiating folds, and I'm taking the square root of a fold. And this gives me back a new fold, which will compute the standard deviation of my input set. And so if I apply this fold to the numbers from 1 to 100, it gives me the standard deviation, which in this case is 28.9. Any other questions before I go on to alternative ways that we can consume folds? No? OK, good. So far, we've only been using this fold function to fold a list, in this case, serially in sequence. But if we actually look at the fold type, right, it doesn't actually care how you use these tally and summarize functions. Right? It says, here you go, do whatever you want with them. And so that's what we're going to do in the next few slides. We're going to do whatever we want with those two functions. The most obvious thing we could do is we could apply that in fold in parallel over the list instead of in one serial pass. So I'm not going to dig into this code other than point out that we just take the list, we break it into chunks, and then we tally and reduce each chunk in parallel. And after we do that, we reduce the final results one more time to get, and then summarize that. And that's how we can process the list in parallel. And this is guaranteed to give the same result as doing the fold serially, one element at a time, thanks to the monoid laws. If you're familiar with the monoid type class in Haskell, one of the laws is that mappend has to be associative. So in that, at a high level, means that the order in which we group mappends will not reduce the result. And that's why this average right here is, in fact, is regrouping the mappends in order so that it can compute things into parallel. And that wouldn't work if we didn't have the monoid guarantees. And then in general, monoids tend to arise a lot in parallel and distributed processing for exactly this reason. And that's why the algebra library in Scala provides lots of monoids, because they're very interested in big data processing. So unfortunately, for the example that I chose, the parallel version is slower, but it is parallel. So in this case, the real time is 2 seconds, but it's actually using 8 seconds worth of CPU time. So it is actually exercising 4 CPUs. The reason why it's slower is because of splitting the list into chunks and then processing each chunk in parallel eliminates shortcut fusion. And you actually get a huge speed up from shortcut fusion, which is like on the order of 10x or 20x faster. And we lose that speed up when we switch to the parallel version. So we got a 4-fold benefit from parallelism, and then a 10-fold slowdown from not getting shortcut fusion, roughly. And that's why this ends up being slower. So on less contrived examples that are more complex, you don't have shortcut fusion in the base case anyway, and then the parallelism actually gives you a benefit. And we actually have real practical experience at work that shows that parallelism does give a real benefit. But for this example, it doesn't, so I apologize. And also, I want to point out that even for this example, right, if we had a machine with more than 7 cores, then this actually would still be a performance improvement. So you don't have to just use folds for parallelism. So another cool thing about folds is that you can use them to fold even impure collections. So a lot of you may be familiar with Haskell's foldable type class, which lets you fold lots of different pure collections in Haskell, like lists or sequences or vectors. But we can use folds to fold the capital F fold to fold impure collections, like a list T. So I just picked one from my own library. It could be any list T package, really. And I show that you can actually implement a fold list T, which, given a fold from I to O, will fold a list T of i's to a monadic result of O. And it will do so efficiently in one pass over the list without leaking space. And it will take into account all the effects along the way. And so we can fold effectful streams this way. So here is like an effectful stream that reads lines from standard input. And then I can fold that standard input stream using the length fold to count how many lines I get from standard input. So again, this is just to prove that it works. If I take 100,000 yeses and I fold them, I get a result of 100. Sorry, 100, is that 10 million? I think that's 10 million result. And what's really neat is that you can actually apply this to any streaming library. So you can use these exact same trick to write folds that work with Conduit or with IO streams or with list-T or machines or pipes or Turtle. Yes, even Turtle has a streaming abstraction. But that's really cool because you can, folds are really portable and reusable. You can, so folds are write once, run everywhere, which you can't even, that's not even true for the foldable type class, but it is true for the capital F fold type. And you also don't need to reduce the entire list to a single value. A very common request in large analytics companies is you want to compute time series of aggregates. So instead, you want to actually partition your input list into buckets, and then you want to fold each bucket. So for example, let's say I have a time series with 8 data points in it. So 0, 1, 2, 3, 4, 5, 6, 7, 8. I can just go ahead and, well, first off, I can just treat each data point as a 1-element bucket. So I just tally that data point. That gives me intermediate result. I do nothing with it. I don't map pend it or anything. And then I just go ahead and summarize it to get the corresponding output for that 1-element input. And then let's say I want a coarser bucketing scheme. So I can partition things into buckets of 2. In this case, now I map pend the 2 intermediate results, and then I summarize each bucket. So this gives me a coarser time series. I can partition things into 4s and do a nice little tree of mappends to get the maximum parallelism. Or I can partition things into 8, and so on. This is a very nice way of creating tunable time series. And what's really nice is that you don't need to decide up front how granular your time series is going to be. You could just, the fold doesn't care, right? These are just values waiting to be waiting to be processed. In fact, what's very common is that when you do initial data collection, you'll store things, you'll just go ahead and take your input and tally it, and you'll give your, let's say you have your most granular data set. And you'll keep that around for just doing very granular time series processing. And then as you begin to run out of space and you want to compress things, and you don't care about more granular time series, you'll then go ahead and compress that to a less granular time series like this. And then as space again continues to run out, you'll compress it further and further if you want to conserve space. Another nice trick about folds is that you can actually delegate fold work across multiple machines. So let's say you have some sort of a client-server architecture. You have some server sitting in a data center at your company, and you have multiple clients. Maybe these are mobile phones that are receiving events from the app that you install on their phone. And so each mobile phone is getting a stream of events, like 0, 1, and 2. And that phone can do the tallying for you. So for each input event, it'll call tally. It will transform the event to its input monoid. So it gives you a bunch of monoids now sitting on this mobile device. And that it doesn't need to necessarily transmit those internal monoids upstream immediately. It can actually do some aggregation on the device ahead of time to compress things and do some work for you. So we can collapse these intermediate monoids to a single monoid on the device and then send that upstream to the server. And the server can then collect monoids from all the different devices and then do some further aggregation on its side and then summarize as necessary. However, what I just described is a trick that only works with a lot of caveats. The first is that this requires a stronger condition, which is that the monoid that you use internally has to be a commutative monoid. The reason why is that you can't really easily order the events coming in from different devices. So you just say, like, you know what? I don't care about the order. Just I'm going to use a monoid that has a mapend operation where the order of its arguments don't matter, and it always gives the same result. And for example, so some of the folds that I gave previously are commutative monoids, other ones are not. An example of a fold that's not a commutative monoid would be the exponential moving average, because there the order of elements matter because you're biased towards more recent elements. Another example of a fold that's where order matters is obviously is head, right? If you want to ask what's the first element, then order definitely matters. So the second caveat is that this requires that you can run Haskell code on your client devices. And if anyone's done mobile programming in Haskell, they know what a big pain in the ass that is. And so finally, you need to slightly tweak the fold type, and you need to add an additional constraint to this internal monoid, which is that it's also serializable and deserializable. And so this is what will allow you to transmit it across the client-server boundary. In practice, this is actually not a big constraint. All the folds that I discussed so far, you can very easily add a binary constraint, and then will all still work. And this works because, again, binary constraint distributes over products and unit. So for example, we can write if pairs, so if A and B are serializable, then a pair of A and B is also serializable. And so that makes sure that the applicative instance that we wrote still type checks. All right, any other questions before I move on to the final portion of the talk? Okay, good. So this is the part that's the most interesting. So as is traditional with the Lens library, you can write a lot of examples which are very short to write, but take a very long time to explain. And so this focus function is no different. So I'm going to walk through it slowly, which is that, so this focus function basically transforms the upstream input of a fold using a lens from the library, or really an optic from the library, because it will work with getters, it will work with lenses, it will work with prisms, it will work with ISOs, it will work with traversals, and I'm probably forgetting a few lens abstractions, but it works with a lot of things in lens. And this is just probably the most specific one that it supports, which is a getting lens, or a getter in lens terminology. And the way it works is actually quite concise. So we take a fold with a tally function, a summarize function. We're not going to change the summarize function, but we will change the tally function. And the way we do it is using this very abstract full map of function, which literally just says, given a function from A to some monoid, I can transform it to a function of B to some monoid. And it uses the lens to do that. And it's just a bunch of new type unwrapping and unwrapping just to make all the types type check. And lens is crazy like that. But this is the one thing you need to keep in mind is that this is a very cheap function. It basically does absolutely no work. But it still lets you transform the input. So for example, let's say I have a fold from some input type to some output type, right? But really, I don't want to consume just i's. I want to consume maybe tuples of i's and some other value. In other words, I want this fold to focus on just the first element of the tuple and ignore the second element of the tuple. And the way I would do that is just writing focus _1, where _1 is a lens from the lens library that focuses on the first element of a tuple. Or another example, let's say I've written a fold that takes i's as input, but really I have a list of maybe i's. So there's some nothings in there and then some justs in there. And I want to tell my fold, you know what, just go ahead and ignore the nothings. I just want you to focus in on the justs. And so the way I can do that is just saying focus _just, where this _just is a prism from the lens library that just looks at the just elements and ignores nothing elements. So here is some real examples to drive home how that works. Let's say I have a list of either ints or strings. So the left values are ints, the right values are strings. So, and then I might want to ask questions like, could you add up all the left integers and ignore all the right values? And this is the way I would write that, is saying, focus on the left values and sum them. And then that will give me 15, because that's 1 plus 4 plus 10. Or I can say, focus on the right values and just count how many of them there were. And so there are 2 right values in that list, so it will return 2. And here's another example. Let's say I have a list of maybe tuples of int and string. And I want to dig in really deep into that to ask questions like, can we just add up these numbers? I don't really care about the justs or nothings. I don't really care about the strings. Oh, sorry, did you have a question?
Could we make a fold that goes over the lefts and the rights at the same time in one pass?
Yes. So the question was, can we write a fold that goes over the left and right elements at the same time in one pass? Yes. And the way we would do that, in fact, that's what this slide originally did, and I split it into 2 smaller examples. So yes, the way you would do that is you would take these 2 folds right here, and then you would use the applicative operations to combine them into a new fold. So if the thing you're interested in is a numeric operation, you would just like add or subtract them directly instead of using applicative operations. But yeah, so if I wanted to get both of these results at the same time, then I would say 2-tuple constructor, the $ brackets, focus left sum, brackety splat, focus right length, and that would give me the derived applicative fold. So let's say now going to this example, let's say I just want to add up these numbers. So I want to focus in on the just, and then I want to further focus in on the first element of the tuple. So I would write focus just.1, and this works because lenses can be composed using function composition, and then compute the product, not the sum. And so 1 times 2 times 5 is 10, so that gives us the right result. And similarly, I can say count how many nothings there are, and there are 2 of them in the list. So you can imagine this is really useful for us at work, because at work we do network security, we do deep packet inspection. We have to parse lots of different protocols, network protocols. So we have lots of situations where we need to dig several protocol layers deep. So we have lenses pointing to lower protocol levels. Or we want to say, I just want to parse TCP sessions, and I want to ignore UDP sessions. So we have prisms pointing to TCP sessions that just go ahead and ignore other sort of IP traffic. And so this lets us dig in really deep into network protocol hierarchies and just fold the things that matter. Because conceptually, if you think in terms of the Unix philosophy, you want to write something that does one thing and does it well. So this product fold just does one thing and does it well, right? It just multiplies numbers. That's all it cares about. It's a multiplying machine, right? It doesn't want to have to think about dealing with tuples or maybes or other sort of records, right? Instead, focus just lets the product focus on what it does best, and then we just adapt that to our data type as necessary. So we don't have to write a product fold for every single data type that we might want to process. We just write one product fold and just reuse it in lots of different contexts. Any questions before I conclude? So like I mentioned, we actually use this trick a lot at work. So we have a large Haskell team at Awake Networks, which is a security company. And one of our Haskell components is high performance network processing for monitoring network packets. And this has to be done in a parallel way. And we use a type similar to the full type, which I presented with some modifications, which are customizing it to our needs. But conceptually, we formulate every analysis of interest on packets as a fold. And if we want to run multiple analyses side by side, we combine them using applicative operations. If we want an analysis to focus deep on something in the network protocol hierarchy, we can use the focus function to focus very deeply. And if we formulate our analyses in terms of monoid, then we get parallelism for free, which is very important to us if we want to keep up with network bandwidth. So I want to conclude by saying we can have one very simple but composable type. It supports applicative operations, numeric operations, parallelism, bucketing and rollups, focusing, and it's portable to any streaming ecosystem. So you don't have to pick or buy into a particular streaming library. And it supports many non-trivial useful analyses. And it'll support more if people can port things from Scala's algebra library to Haskell. And so I think that concludes my talk.